5.4, an introduction to the inverse trigonometric functions. In this unit, one of the key things will be understanding and recalling your all students take calculus components, remembering where the different trig functions are positive and where they happen to be negative based on quadrants. That's going to be one of the key things that we'll work with in this unit. To start with, we have just our good old reference table that we used in our last section and our last unit test. These were a series of popular quadrant 1 reference angles. We had an angle, we looked up a trig value. Now we have a series of questions that ask us to kind of work in the opposite direction. So what I asked to begin with is, use this table and answer the following questions, given the answers in both radians and degrees. What angle theta would satisfy the following equations? Sine of theta equals 1/2. Well, if we go and use our lookup table, sine of theta, there's an example of where sine of theta equals 1/2, and we find that's true for 30 degrees or pi over 6 radians. Where's the tangent equal to 1? Tangent 1, 45 degrees, pi over 4. Where's the cosine equal to the square root of 3 over 2? 60 degrees, pi over 3 radians. Oh, excuse me, cosine equal to square root of 3 over 2. My fault, looked in the wrong place, apologize. Square root of 3 over 2 for the cosine, 30 degrees or pi over 6. Notice all these answers are what? We've talked about this before. They're all coming from quadrant 1 angles. They're all positive numbers. And what we've done here is we've solved inverse trigonometric equations. In our previous unit, what we've seen is we're always working with something of this nature. A trigonometric function with an input being an angle in either radians or degrees, and it produces a value for us. Excuse me. Now, the practice questions that we just did the other thing. They give us an answer from a trigonometric function, and they ask us what angle value produced that. Answer could come across in either degrees or radians. And so that's what we're going to be working with as we work through this entirety of this unit, section 5.4 through 5.6. We're going to start answering the questions, what angle is involved? In the past, we've used an angle to figure out how long some sides are. Now we're going to work in the opposite direction. So previously, trig, angle, equal value. Now, inverse trig, value, equal angle. That's going to help us with the three main inverse trigonometric functions that come off the big three of the trig functions, sine, cosine, and tangent. And we're going to start answering questions such as the following. What are the angles in a right triangle that has sides of length 6, 8, 10? A 24-foot ladder leans against a house. It touches 18 feet up against the side of the house. What's the angle of elevation? What's the angle that the ladder makes with the ground? Identify two angles between 0 and 360 degrees that satisfy the equation sine of theta equals 0.607. These are the kind of things that we're going to go ahead and walk our way through in this unit. And one of the important pieces that we'll talk about, and this is what your preparation work was from after the last test with that short homework problem, is the concept of an inverse function. We would like our inverse, which is nothing more than what? Flipping the x and y values of an existing function. We want our inverse to be a function itself. And if you recall from way back when, the way for this to happen is for our original function to be 1-to-1. Passing both the vertical line test, which it has to do in order to be a function, but also passing the horizontal line test. And we said a 1-to-1 function is one such that it passes both the vertical and horizontal line test, and therefore guarantees that its inverse will also be a function. Think about it. If you pass the horizontal line test, your inverse will pass the vertical line test and therefore be a function. And so what we focused on just as we began were a couple of basic pieces here. I gave you on your notes the graphs of the sine, cosine, and tangent functions. And on your notes, it was a little bit hard to see, but there were actually some pieces that are very faint here, but you could actually see. I'm just going to go ahead and kind of dash them. There was more of the graph. I'll do this for cosine function as well. and then also for the tangent function. And again, just because you don't have a color copier, it's a little bit harder to see here on the notes. But that original, these dashed functions, while they certainly passed the vertical line test, they flunked the horizontal line test. How do we fix that? By restricting the domain. And so what you see on your notes are restricted domains. I've taken the sine function and I'm only going to look in this little solid area. This solid area for the cosine. This solid area for the tangent function. And as soon as I look just in those little restricted areas, not only do I pass the vertical line test, I pass the horizontal line test as well. And therefore, I now have an inverse that will be a function itself. So over here, what I've done with the sine function, I've restricted the domain to run from negative pi over 2 to positive pi over 2. Notice how I put brackets around it. And my output values run from negative 1 to positive 1. On the cosine side, when I restrict it, I'm going to run from 0 to pi. And my range is also going to run from negative 1 to 1. And when I work with my tangent function, just work in the area that I see, I'm going to be between negative pi over 2 and pi over 2. Notice how I put parentheses around both of those, and my range is going to be all real numbers. And so by doing this, restricting these three functions to these little domains, restricting the domain, I've now created a one-to-one function, and I'm going to have an inverse that is a function as well. And so what you see is, down here, those three graphs that have been highlighted and just kind of bolded in your notes have now been flipped. The x and y coordinates have been interchanged. I've built the inverse. And what you should notice on all three of these, they pass the vertical line test. These inverses are functions. And so what you see is the inverse sine function. Notice the negative 1 superscript. You also see this language arc for the different inverse functions, but typically you're just going to see the negative 1 superscript out here. The inverse sine function, the inverse cosine function, the inverse tangent function. And quite simply, all you need to do, I'm going to save myself just a little bit of writing and video time here, is the domain of the original sine function becomes the range of the inverse sine function. The range of sine becomes the domain of inverse sine. And so you can fill those pieces out just as you go. Now there's a couple important things that are worth noting as we look at these inverse functions. First things first, think about the three ranges. Those are all the answer values that your functions are going to give you. The inverse sine function is going to return angles from negative pi over 2 to pi over 2 radians. That's where all the answers live, or between negative 90 and positive 90 degrees. That same thing applies for the tangent function. It's going to return angles. It's going to return answers between negative pi over 2 and pi over 2, negative 90 to 90. And the cosine is going to return answers that run from 0 to pi radians, or 0 to 180 degrees. This is an important fact. Make sure you get this down and are comfortable with it. Know where the answers for these functions come from. Now, the next thing that we gave you, and we talked about it in class, we'll have to do a little bit of work here again because we don't have a color copier, is that same thing on the last page can be used to represent the following statement. I'm going to show you just a colored version just as well. So there we've got to go. This will help a little bit and you can kind of fill this in. What I'm trying to show is, there we go, that the inverse sine function is going to return answers in either quadrant 4 or quadrant 1. So you can go ahead and highlight those two. The inverse cosine function is going to provide you answers in either quadrant 1 or quadrant 2. The inverse tangent function, just like the inverse sine function, is going to provide you answers in either quadrant 1 or quadrant 4. Now here's the other important thing. Anytime you put a positive input into any of the inverse functions, any of these three inverse trigonometric functions, they will always give you an answer in quadrant 1. Positive value going into any of the three inverse trig functions always gives you an answer in quadrant 1. If you have a negative output given to either the inverse sine or the inverse cosine function. Sorry, let me just move for a second. These two functions, you're always going to get an answer in quadrant 4. And one other important thing, that answer is going to be a negative angle value. The inverse sine, inverse tangent. If you put a negative input value, you're going to get an answer in quadrant 4 expressed as a negative angle. So instead of seeing 330 degrees as an example, you're going to see the calculator give you an answer of negative 30 degrees. That would be true for these two functions, inverse sine and inverse tangent. If you put a negative value into the inverse cosine function, it's going to give you an answer in quadrant 2. Answer in quadrant 2. So make sure that you are very, very comfortable with this. One other point. An answer that you get in quadrant 1 to an inverse trig function is a reference angle. Remember, all angles in quadrant 1 serve as reference angles. They're going to have partners in other locations. That's going to be very valuable to us as well. So there's two more pieces that we're just going to cover in this first part, and that's to recall your reference angles. Understand how reference angle works in both degrees and radians. These are formulas that you've seen before. They're repeated for you one more time. How do I find reference angles, and how do I find an angle that owns a particular reference angle? They're just variations on the same theme. Know these formulas. Know how to calculate a reference angle. Know how to determine an angle that possesses a given reference angle. And as we wrap up this part of the video, we're going to do this with our last problem here. List 4 angles, one in each quadrant, that have a reference angle of 45 degrees. Well, in quadrant 1, that is nothing more than 45 degrees. You're your own reference angle. In quadrant 2, let's visualize this. 45-degree reference angle that would live right in there, right inside the bow tie, requires an angle that's equal to 180 minus 45. Q2, 180 minus 45 equals 135 degrees. In quadrant 3, for this reference angle to be 45 degrees, I would need an angle 180 plus 45. Quadrant 3, 180 plus 45 equals 225 degrees. And finally, in quadrant 4, I'm going to need an angle that's equal to 360 minus 45, or 315 degrees. Remember, we talked about symmetry partners before. 45 degrees, 135, 225, 315. They all have 45 degrees as their reference angle. Now, other questions. Which of these 4 angles would satisfy the sine of theta equals square root of 2 over 2? Well, we know that the sine function is positive in quadrant 1 and quadrant 2. The sine of 45 degrees is square root of 2 over 2. And by the way, in quadrant 2, what angle also shares 45 as its reference angle? 135 degrees. What angles would satisfy sine of theta equal negative root 2 over 2? That would be in quadrants 3 and 4, 225 degrees and 315 degrees. Remember, our reference table would tell us what? Hey, go look up 45 degrees, figure out what its sine is. The sine of 45 degrees is root 2 over 2. And that's how we walked into these other pieces. So to start getting a feel for this unit, what's the key? Understand reference angle concepts. Know where sine, cosine, and tangent, where they happen to be positive, where they happen to be negative. We'll talk a little bit more about the specific values that our calculator produces in the second part of this video lesson, and we'll move to that in a few moments. This will end part 1. Second part of the 5.4 lesson, we're going to work with the last 3 pages of the notepad. And what we're going to be looking for first is problem number 6, or example number 6. We're going to use the table of special values to go ahead and find the value of these various inverse trigonometric functions. We're going to identify the quadrant in which the answer needs to come from, and we're going to express our answer in radians for this problem. The first says, I want to find the inverse sine of 1/2. What's nice about this, and for that matter, part C as well, is look, our input value to those two problems is a positive number. That tells us that our answers are going to come back in quadrant 1. Remember, anytime you put a positive number as input to an inverse trigonometric function, you're going to get an answer that's an angle in quadrant 1. The other places we'll talk about in a second, but let's go ahead and work A and C. Our angle comes from quadrant 1. Great. It means we can walk right to our table and just simply do a straight lookup. Who has a sine equal to 1/2? It turns out it's pi over 6 radians. So I'll go ahead and just move the table here so we'll have something to work with. 30 degrees, sine, pi over 6 radians is what we really want to work, is 1/2. This answer is pi over 6. Who has a tangent equal to 1? There's our tangent, there's the 1, pi over 4 radians. Now, let's do some other work with the other problems. They all have negative input values. What's that mean? Well, remember, we talked about the places where the inverse function give you their answers from. Positive input always gives you a quadrant 1 angle, no matter which inverse trig function you're working with. In terms of the cosine function, when you give it a negative value, negative input value, your angle is going to come from quadrant 2. Same thing here, inverse cosine. That's going to be a quadrant 2 angle. Inverse sine, inverse tangent, when we put a negative number, negative square root of 3 over 2, negative 1. Those answers are going to come from quadrant 4. And by the way, they are going to be negative numbers. Negative numbers. We talked about this before. The range of these functions, what they happen to be. So, how can we solve this? Well, I know my angle needs to be in quadrant 2, but what I could do is use a lookup value, go ahead and get a reference angle, and say theta r equals the inverse cosine of positive root 2 over 2. That's going to get me a nice first quadrant angle, a reference angle, and gee whiz, that reference angle is going to be consistent with my angle in quadrant 2. What do I know? The reference angle here, square root of 2 over 2, it turns out to be pi over 4 radians. My angle needs to live in quadrant 2, and it has to have a, has to have a reference value of pi over 4. Symmetry tells me that is pi minus pi over 4, or 3 pi over 4. My angle is 3 pi over 4 radians. Test it out in your calculator if you want. For a cosine, inverse cosine of negative 1, well, my answer is going to come from quadrant 2. I can figure out who has an inverse cosine of 1. Turns out that's 0 degrees. Who's a symmetry partner with 0 degrees? There's quadrant 1. It must be this angle that lives in quadrant 2, which happens to be pi radians. Theta equals pi. Inverse sine of negative root 3 over 2. This needs to be a quadrant 4 angle, and it needs to be a negative value. So take a look. Inverse sine of the square root of 3 over 2 happens to be pi over 3 radians. Now, in quadrant 4, going to do two things here because we're working with the inverse sine function. Remember, we have to give a negative answer. But let's use our reference angle formula real quick. In Q4, we'd have what? 2 pi minus pi over 3 to get our angle, 5 pi over 3. Well, 5 pi over 3 certainly isn't a negative number. How can we make it negative? Simply subtract 2 pi. 5 pi over 3 minus 2 pi, negative pi over 3. There's our official answer to the inverse sine of negative square root of 3 over 2. And when we look at our last problem, inverse tangent of negative 1, again, quadrant 4 has to be a negative angle. Well, how can we work that? Who has a inverse tangent equal to 1? Pi over 4 radians. There is our reference angle, pi over 4 reference angle. we need a angle in quadrant 4 that has pi over 4 as its reference angle. That turns out to be 2 pi minus pi over 4. 8 pi over 4 minus pi over 4. 7 pi over 4. Again, that's not too good for us. How come? We need to get the official answer has to be negative. That's what the inverse sine tangent function is going to produce. If we get a quadrant 4 angle, we have to express it as a negative value. And if I do 7 pi over 4 minus 2 pi, that's going to give me what? Negative pi over 4. So there's kind of an interesting side note to put aside, and this will be something that's helpful for us. When we're working with one of these functions, if we get theta r equals, let's say, pi over 4, and we want to calculate the quadrant 4 angle, it turns out it's nothing more than theta equals negative pi over 4. Let's show how that happens one more time. Well, we said our reference angle formula is nothing more than 2 pi minus pi over 4. By the way, take a note of the following. What do you see this angle? Negative pi over 4. Look at these two angles. They're separated by how much? How far apart are they? Well, this one is 2 pi bigger than negative pi over 4. 2 pi minus pi over 4 minus pi over 4 separated by 2 pi. And what does that tell you? 2 pi minus pi over 4, or 7 pi over 4, is exactly coterminal with negative pi over 4. So if you're working with the official inverse tan or inverse sine, and you're putting in a negative value, all you got to do is the following. Calculate theta r, and then your quadrant 4 value, all you have to do is make that reference angle negative, and you'll get your other version. Another example, let's say we have theta r equals pi over 6, and we need a quadrant 4 answer. For our inverse function, all we have to say is negative pi over 6. So that's kind of the process to work with here on these problems. I am not going to work through example number 8 because it uses the exact same concepts except what? All 6 problems are the same except you're working in degrees rather than radians. Very quickly, we're going to work with problem number 7, which is looking for some exact values. We can't use our table of special values this time. Why? Because we have, I guess for lack of a better term, remember I called all these kind of the popular angles? Well, we're going to find some of these are unpopular angles. How do I solve this? Well, we want all our answers in radians, so let me make sure on my calculator that I'm in radians mode, which I'm not, but I will be. And let's do the following. Inverse sine, second, sine, negative 0.8. By the way, we should get a quadrant 4 answer. It should be a negative number, and it sure is. Oops, I'm in degree mode. Let me fix myself. So I'm supposed to give these answers in radians, my fault. Now I'm in radian mode. Let's rerun inverse sine, negative 0.8, negative 0.927 radians. Let's work the last problem, tangent, inverse tangent of 3. Here we go. Should be getting what type of angle this time? Should be a quadrant 1 result because I have 3, positive number going in. And I sure do, 1.249 radians. Inverse cosine of 3. Error domain. Why? Because there is no such value. Remember, the range of the domain of the inverse cosine function runs from 0 to pi. We're much different here. We're coming out with a totally unacceptable value here. And that's why we get a domain error. 3 is not part of the domain of the inverse function. Go back and look at your notes, and specifically what you'll find is that the domain of the inverse cosine function runs from -1 to 1. 3 certainly doesn't fit in that. That's why we get a domain error. It's an important thing to note, and we'll come back to this down the road. All right, so let's work through one more set of problems. In our prior example, we computed what I like to call the official, the calculator version of those three functions is the official values. Now we're going to come up with a different way of looking things. Remember, number one, the inverse function only is going to provide you with one answer. But because of the concept of symmetry and coterminals, there's many, many angles that share the same trigonometric value. And we're going to prove that as we work through this set of examples down here. First question, they want to find all angles between 0 and 360 that have a cosine that's equal to negative square root of 2 over 2. Well, what's a couple things we know? We know the cosine is negative in quadrant 2 and quadrant 3. That's where our answers are going to come from. And if we use our special tables value, we'll find something very nice. We're going to find that if we look up the square root of 2 over 2, in other words, let's build ourselves a reference angle. Who has an inverse cosine of square root of 2 over 2? We're going to give all our answers this time in degrees mode. So make sure as you work this that you put your calculator into degrees mode. My question again is, who happens to have a cosine that's equal to the square root of 2 over 2? Our lucky little lookup table tells us that that's 45 degrees. Now, 45 degrees is a reference angle. It's quadrant 1. The cosine of 45 degrees is positive square root of 2 over 2. We want angles in quadrant 2 and quadrant 3. And we're going to use our reference angle of 45 to help us find those partners in the other quadrant. In quadrant 2, our angle that will do the job is 180 minus 45 degrees, 135 degrees. In quadrant 3, 180 plus 45 degrees, 225 degrees. We found our two answers. All answers between 0 and 360. Sine of theta equals 0.9659. Where is the sign positive? Quadrant 1, quadrant 2. Reference angle theta r equals sine inverse sine of 0.9659. Let's run it through the calculator. Inverse sine 0.9659. Oops. Inverse sine 0.9659. Sorry for the finger click there. And we get 74.99, essentially 75 degrees. Well, where do we want our angles to live? We want them to live in quadrant 1. And, sorry about this as I get a cord out of the way. Want our angles to live in quadrant 1 and quadrant 2. Our quadrant 1 answer is already the reference angle. That's the nice thing. Quadrant 2, 180 minus 75 degrees, 105 degrees. You can test. Run the sine of 75, run the cosine of 105 degrees. You're going to get a number just like that. Let's stay on this side. Cosine of theta. Any angle between 0 and 360 that has a cosine equal to 0.2924. Quadrant 1, quadrant 4. Starting point, theta r equals inverse cosine 0.2924. Let's run it. Inverse cosine 0.2924. Just about 73 degrees. We live in which quadrants? Quadrant 1. Hey, I already got my answer. Quadrant 4. 360 minus 73 equals 287 degrees. So let's work a few more